Hello everyone and welcome back to another mathematics tutorial. Today I'm going to talk about open and closed sets in metric spaces. Now I'll jump straight in with the definition of an open set. So on the screen here I've said let XD be a metric space and U a subset of X. Okay, so U is some subset of X. Now we say, so this is our definition, U is open. So U is open, underline that there, open, if, so we're going to have a condition now, so if for every y in U there exists r greater than 0, so some positive number, such that the ball with radius r centered at y is contained within U. Okay, and remember that this ball here is the set of points whose distance from y is less than r. So it's the set of points P such that d of py is less than r. Okay, and we want that ball to be contained within U. So thinking about this as an example now, as a bit more of a graphical illustration, let's say we have x, which is some crazy set here. So this is x, and U is everything inside this line here. So this is U. Then, given any point that I pick in U, I can fit some small ball around it. Okay, so no matter how close I get to the edge, I can still fit in a tiny ball as long as I stay close enough away from that edge. So even if I go right up to the end, there's still a tiny spot for me to squeeze a ball in. Okay? So that is an open set where, given any point in that set, you can fit some ball around it that's still contained within that set. Now, the best way to understand this is through some examples, because the open sets are going to look a lot different depending on what metric space you're looking at. So if we take x is the real line, and d of xy is modulus x minus y, then we can consider some examples. So let's take U to be the set 0, 2. Okay, so let's have a look at our number line. Here is 0, here is 2, and U is everything in between, but excluding the endpoints. And you can see that U is open, because if you pick something in U, so something in here, then you'll be able to fit some ball around it, as long as you stay away from these edges, so you can fit some small ball around it here. So it's worth remembering here that in this case, the open balls are going to be intervals. Okay, so here, given any point x and any radius r, it's going to be the set of points y in R such that modulus x minus y is less than 2. So it's an interval. It's essentially saying that y is between, if you just take the modulus out, then you can rearrange it to get it as an interval. Okay? So in this case, the open balls are intervals, and we can see that we can squeeze in some interval here, no matter what point we choose. So if we pick a point here, we still squeeze in some interval. Okay? So that's a nice example there. Now let's try an example of a set that is not open. Okay? So let's try U is equal to 0, 2, but it's closed at 2, so we include 2. Okay, so we have our same situation here. So 0 here, but 2 here, and we include 2. Now it's not open, because sure, we're fine if I go in between, but if I go at 2, then I can't fit in an open ball or an interval here, because I go outside of my set U. So that's the important bit. You have to keep your open ball inside of your set U, and that has to hold for every point in the set. Let's try another one. How about let's keep the same space, but I'm going to change the metric now. So this time we're going to look at our friend, the discrete metric. So it's 1 if x is not equal to y, and 0 if x is equal to y. Okay, now what do we get? Well, let's take a subset of x, a. Okay, so it's a subset of x, so it's a subset of the real numbers. Is it open? Well, actually, yes, every set is open here. And the reason for that is if you were to, you know, just pick y in A and just choose r is equal to a half. Okay? Then the ball with radius a half centered at y is just y. Right? Because this distance, the only way it can be less than a half is if it's 0, and then you know that the point has to be equal to y. So this identity holds, this equality holds, and we know that that is going to be contained within A by definition because y is in A. So A is open, so every set is open. So this is something interesting here. The discrete metric makes every set open. Okay, now let's have a look at closed sets. So you might have an idea of what a closed set might be, but let's take U, a subset of X, is closed if X without U is open. Now, as a reminder, you may have seen this before, you may not have seen it before, but x without u is written x minus u, and that is the set of points P in X such that P does not belong to U. So that's everything in X that's not in U. Okay? So we say the set is closed if, when you look at the stuff that isn't in that set, you want that set to be open. Okay? So it's kind of looking at, you know, it seems a bit unintuitive at first, but it does work out quite well. So let's think about this with some examples. Again, examples are always the best way to learn things in maths. That and solving problems on your own, but that's obviously a bit harder. So let's consider the real line again. So the real line and the metric is just the standard metric as usual. And this time U is going to be the set 0. Okay, it's just 0. Okay, is it closed? Well, yes, it's closed, because if we look at R without U, then that is just going to be equal to the set of points P in R such that P is not 0. So it's essentially minus infinity, 0, union, 0 to infinity. So it's everything that's greater than 0 or less than 0. And this is open, because if I'll show you with a picture here, to make it easier to visualize. Here's 0. We're forgetting about 0, so forgetting about 0. And we're just looking at stuff that's down here and over here. And if we pick any point, we'll be able to fit some interval around it that doesn't come back to 0. Just make it small enough. So this R without U is going to be open, and therefore U is closed. So it's important to remember here that closed means you have to look at the stuff that's not in U. Okay? If you want to look at open, you need to look at the points that are in U, and if it's closed, you need to be thinking about the points that are not in U. Okay? And you can see some other examples as well. So you can take any interval, so you can take U to be, say, 0, 2. This is also closed, which should be fairly easy to see, because You know, if you have, let's say we have 0 here and 2 here, then, you know, you're thinking about stuff that's down here or up here, then that's going to be open if you think about R without U. Okay? So this is closed. Now, here comes a slightly interesting remark. It's important to remember that U is not a door. Okay, U is not a door. And what do I mean by that? Well, if you think about a door is either open or closed. It can't be both. It's going to be open or it's closed. But sets don't just have to be one or the other. So U can be open and closed. Okay? That may seem very strange at first, but it is true, and I can show you a nice example. So what if we take e.g. in R, in the real line, with the standard modulus metric, we can take U to be the entire set. Okay, so U is the whole real line, and then R minus U is the empty set. Okay, and the empty set is open because we have this statement for all y in the empty set, and that is trivially going to be true because there is nothing in the empty set. So this is what's known as a trivial truth because there's nothing to check, essentially. There are no elements to check. So this is going to be open, so it's definitely closed. Okay, so U is R minus U is open, and U is therefore closed. But also, U is open, because if you pick anything in R, then the ball is going to be contained within it. So let me write here, so U is closed, good. But, given, let's say, Z in U, which is the whole real line, then the ball of any radius for that matter, centered at Z, is contained within R, by definition, of the open ball, and R is just equal to U. So U is open as well. So U is open and closed. Okay, so you may have to think about this for a little while, but something can be open and closed. And, furthermore, it can be not open and not closed. So if I take U is equal to 0, 1, but we include 1, then U is not open, because we have this problem at 1. Okay, so here is 0, everything's fine there. But here is 1, we include 1. So when I pick 1, I can't fit that interval, that ball in. So U is not open. But U is not closed. Because R without U, well, it's going to be the set of points that are not in here. So if we write that down, that's the set of points P in R, such that, well, we can be P is less than or equal to 0, or P is greater than 1, and this set is not open, because we have a problem at 0 here. So if I draw this, we've got 0 here, and 1 here. So we're looking at everything larger than 1 and everything less than or equal to 0. But if I pick 0, can't fit that interval in, because now I've gone back into here. So this set is not open, and therefore U is not closed. Okay? So in this case, U is not open, and it's not closed. It's neither. So this is an interesting case of sets can be open and closed, or neither, or just one or the other, depending on what set you look at. Okay, so that's all I wanted to talk about. Remember that open sets, you want to look at all the points in that set and be able to draw a ball around them. And a closed set, you're looking at the stuff that's not in that set, and you want that new set to be open. Okay, so just a reminder, closed means x minus u is open, so the opposite set, if you like. Okay, so that concludes my video. If you haven't seen my previous videos on open balls or metric spaces, I suggest you check those out, because this may have been a bit confusing if you haven't. So do check out the link provided, and it will take you to topics on that. Don't forget to subscribe, and I'll see you next time.